Good morning everyone. This is Dr. N. Ramya, Assistant Professor, Civil Engineering Department. Today I am here to give a lecture on measurement of viscosity. So here already we have gone through the viscous fluids, right? So here the measuring devices, whatever the devices which are used to measure the viscous nature or viscosity of the fluid, that instrument we are calling as a viscometers. The device which is used for the measurement of viscosity is a viscometer. So here for measuring the viscosity, there are 4 methods. Here we are discussing, right? First method is a capillary tube method, rotating cylinder method. Third one is falling sphere method and reflex viscometer. These are the 4 methods we are here to determine the coefficient of viscosity of the fluid. So here we see the first one. First one is a capillary tube viscometer. So here in this method, Hagen-Poiseuille's equation is coming into picture. This already we have derived in second lecture. Hagen-Poiseuille's equation, that for laminar flow through circular pipes. So that method we use here for the measurement of viscosity. That method we are calling as a capillary tube viscometer. So here one tank is there. To that tank pipe is attached to this, and to this pipe we are seeing one piezometer. This is the piezometer and this is the tank and this is a capillary tube. That is laminar flow which is flowing in this circular pipe. And from these another measurement tank is there which is collecting the fluid which is coming from the pipe, circular pipe, right? So the tank which is this tank is collecting the fluid which we have to measure the viscous nature or viscosity of that fluid. And here H is the piezometer height. It is giving the how much head is there at the point and other is at the end. So the distance between these H is L. So H is what? Difference of the pressure head for the length L, and mu is the coefficient of viscosity which we are finding here, and W is the weight density of the liquid, that is rho G, right? This is what a picture is. So here is the procedure, right? This capillary tube is viscometer consisting of a tank, as we have seen. To that tank a tube diameter of length L is attached horizontally to the very close to the bottom of the tank. The circular pipe is attached to the tank very close to the bottom of the tank, and the tube is allowed to the discharge flow freely into the atmosphere. So the liquid is collected into the measuring tank. So here at the end, whatever the fluid is coming from this pipe, there is another collecting tank is there. So that collecting tank is collecting the fluid which is coming from this tank, from this circular pipe. So the rate of fluid collected in the tank per second, whatever the amount of fluid is collected in this tank, from this tank we determine what the viscosity is. The pressure head is measured at the point far away from the tank. Here we have seen one pressure head piezometer that will give you the pressure head. So from all these, whatever the amount of fluid is collected at the measuring jar, right, and whatever the pressure head at this point the piezometer is giving. So all these, from all these parameters we solve the what is the viscosity. We can derive the what is the viscosity of the fluid in the tank, right? So here the Hagen-Poiseuille's the equation, that is H is equal to 32 mu U bar L by W D square. This is the Hagen-Poiseuille's equation, right? And also we have seen that U average is equal to Q by A. Q by area of this pi by 4 D square, right? So here in the place of in the place of U bar, we are substituting this U, that is U bar, that is Q by area. So here the H is equal to 32 mu U bar is Q L by W d square into pi by 4 d square. Right? This is what. So from this, when you do simplification, you will get H is equal to 128 mu Q by pi W d square. So when you do this completely, you will get 128 mu Q by pi W d to the power of 4. Right? So here, and L is also there here. Right? So here, mu. So we are finding the measurement of viscosity, right? Here we are finding the viscosity. So the viscosity from this equation, I am taking out mu out here. The H is equal to 128 mu QL by pi WD to the power of 4. So from these, I am taking mu on the left hand side, that is mu is equal to all to the other side, right? Mu is equal to pi WD to the power of 4H by 128 QL. This is what the viscosity of the fluid. The viscosity of the fluid which is there in the tank. Right? This is the one method. This is the method one, that is capillary tube method. So already we are aware of laminar flow through circular pipe, that already we know that H is equal to 32 mu U bar by WD to the power of square, right? So by knowing this, easily we can find out the viscosity of the fluid. This is a capillary tube method. And another method is a rotating cylinder method, right? Rotating cylinder method. So here, in this method, here we are using Newton's law of viscosity. Already we know what is Newton's law of viscosity is, right? That is, tau is equal to mu into du by dy is Newton's law of viscosity, right? So tau, shear stress, is equal to mu into du by dy, right? Here we are using this Newton's law of viscosity to measure the viscosity of the fluid, right? To measure the viscosity of the fluid. So here, to determine the viscosity of the fluid, here we are taking two concentric cylinders. And the angular space between them is two concentric cylinders. One cylinder is in this and another cylinder is outer cylinder, inner cylinder and outer cylinder. In between these two, space is filled with fluid which we want to measure the viscosity. The fluid which we want to measure the viscosity, right? So the space between these two cylinders, we are calling it as an annual space. The outer cylinder is rotated. This outer cylinder is rotating with a constant angular velocity omega. This outer cylinder is rotating with some velocity, angular velocity, that is omega, with respect to the inner stationary cylinder, right? So here, this is what the diagram is. So this is the outer cylinder and this is the inner cylinder, right? The outer cylinder radius is R2 and inner cylinder radius is R1. In between these, R2 minus R1 is T. R2 minus R1 is T. Right? This outer one is rotating with some constant angular velocity omega. Right? With this effect, what velocity is moving with the outer cylinder, the fluid is there in between these two concentric, in between annular space. So with this velocity, the inner fluid or inner cylinder also starts moving. So that with how much speed the inner cylinder is moving with this outer cylinder. By this method, we can find out the viscous nature of the fluid inside the annular space. The outer cylinder is moving. With this outer cylinder rotation, the fluid inside that also starts make to rotate the inner cylinder, right? So how, with what values we see here, the torque is transmitted by the enclosed liquid to the stationary cylinder. Whatever the torque is generated in the in the fluid, so that liquid starts rotating the stationary cylinder, right? That is the retraining the spring attached to the top of the inner cylinder. So here also, according to the Newton's law of viscosity, tau is equal to mu into du by dy. Tau is equal to mu into du by dy. So since the annular space already we have told you that T is equal to R2 minus R1, the small space, annular space. Yes, this is T. Is quite small at the radius of the outer and inner cylinder, right? Now here, velocity gradient, tau is equal to mu into du by dy. So here I'm taking velocity gradient, du by dy, that is equal to v by t. V by t. So here I'm writing 2 pi r2n, means outer R2. R2 is distance. This one is R1 and this is the R2, right? This R2 is rotating with some angular velocity, right? So that I'm writing 2 pi R2n by 60 t. T, it is there here, t, by t, right? So what is n here? N is the rotating speed of the outer cylinder in RPM. Is rotation per minute. So here, shear stress, in place of dou u by dou t, I am writing complete this term, 2 pi r2n by 60 t, right? So mu into 2 pi r2n by 60 and here into 2 pi r. This complete into 2 pi r, shear stress. Here viscous drag force is what? Shear stress into area. So shear stress is what here? Shear stress is equal to shear force by area, right? Shear stress is equal to shear force by area. So here viscous drag writing as shear stress into area. So already we know the shear stress is this, mu into 2 pi r2n by 60 t and into this is area, 2 pi r1 h, right? So we know that h is the height of the liquid in the annular space, right? So here viscous torque is what? Viscous drag into radius. So here mu, already this complete is there, right? Mu into 2 pi r2n into 2 pi r1h into r1. This way I am multiplying r1 by 60. It is already exist in the previous equation, right? So in this equation I am writing all together, that is what? Mu pi square, 2 pi square r1 2 times r1 square r2 h n by this 4 by 60. Yes, 4 15s are right, for 115 t. So here I am getting that mu pi square r1 square r2 h into n by 15 t, right? R. Here from these I need mu, viscosity. So here I am taking mu on the left hand side and all the terms on right hand side. So here mu is equal to all the other terms, that is what? 15 t capital T by mu into pi square r1 square r2 h capital N, right? All other things. This is what here viscosity by rotating cylinder method, right? This is what is for calibrating the viscosity for a given speed of rotation n. This is a rotation, another method to calculate the measurement of viscosity, right? Here is the third method, that is falling sphere method. Here falling sphere method is, when we hear this falling sphere method, we will get to remember that the Stokes law, right? Stokes law. What is Stokes law? Whenever we drop a sphere into a liquid, with what velocity that sphere is moving in the liquid, right? From these, how much speed it is moving. By this, we can find out the viscous nature of the fluid. If when you drop a sphere, if the sphere is moving very fast, then we can say that the viscous nature is less. If the falling sphere is moving very fast, then we say that viscous nature is less. If it is moving very slowly, then we say that it is having more viscous nature. The fluid is having very high viscous nature, right? So this is what a Stokes law. So when, right, falling sphere is measuring by based on this Stokes law. Here a small sphere is releasing into the liquid, which we are going to find out the viscosity, right? And the ball, when you sphere is dropped in the liquid, that will move with the gravitational force, right? Until it reaches the terminal velocity. The terminal velocity means what? When the buoyant force and the viscous drag force balance with the gravitational force, right? Buoyant force, buoyancy forces and viscous forces when balanced with the gravitational force, then the movement of the sphere moving with, we call it as a terminal velocity, right? The sphere, when it gets balanced, then the velocity sphere is moving, we call as a terminal velocity, right? So here is the rock. This is the liquid which we are going to find out, right? So in this liquid, I am dropping tested liquid. If this is a normal constant temperature bath. This liquid, which we are going to find out the viscosity, right? In this liquid, I am dropping a sphere. So when these forces gets equal, weight is equal to FB plus FD, drag force or buoyancy forces. When these combination of these forces becomes equal with the weight of the sphere, right? We call that sphere moving with the terminal velocity. Terminal velocity, right? So this is what, from here to here, they have taken the length L. This is the velocity V. So now we see how we calculate the viscosity from the sphere, right? W is the weight, has the vertically it is coming downwards, and B is the buoyancy force, vertically upwards, and drag force is also vertically upwards. Two forces acting on a sphere, right? So here this is what common, that's weight is equal to equilibrium condition, weight is equal to drag force plus buoyancy forces. So I need here drag force, that is equal to weight minus buoyancy force, right? We know that drag force is 3 pi mu Vd. 3 pi mu is Fd. Drag force, that is equal to weight pi by 6 d cube, density of the liquid, specific gravity into G, minus pi by 6 d cube, density into G, right? This is the liquid which we are going to find. Yes, this is a standard liquid. So pi by 6 d cube G into pi s minus rho s minus rho f r. This is what we got from this complete. I am taking mu on the left hand side, that is equal to mu is equal to, and everything on right hand side, right? So pi by 6 d cube G rho s minus rho f by 3 pi Vd, right? So this is the equation. From this equation, we are finding the viscosity of the fluid, right? Now another method. See, here are the terms. D is the diameter of the spherical ball, and L is the length, the distance between the sphere starting dropping and at the end certain length L, and D is the time of the sphere, with how much time it is taking to drop from one point to other point, and is rho is density of the sphere and rho f is density of the fluid which we are going to measure, and W is the density weight of the sphere, that is rho g. And here Fb is equal to buoyancy forces and Fd drag force. Mu is dynamic density of the dynamic viscosity of the fluid which we are going to determine, which we are going to test. Right? Here the Stokes law is essentially valid for Reynolds number. It is which is having below 0.1, where the walls has no effect on the terminal fall velocity. It is very important one, right? So it is, see here the weight is equally equating with the two drag forces and buoyancy forces. Here where Fg is equal to Fd plus Fb, right? And here another method, Flex Viscometer. In Flex Viscometer, the viscosity is determined by noting the time of Flex under specific conditions for a fixed volume of the fluid. Here, this also we call it as Flex Viscometer, also we can call as a Seybold, a Redout and Eagle is based on the principle. Right? Here, this is the experiment, this is the setup. See, here is the constant temperature bath, and here inside this U-tube, here we are seeing one liquid, that which we are going to measure the viscosity, right? Here is the small capillary tube. Here is the measuring cylinder. This is what the setup for Seybold Viscometer. So whenever we see that with respect to time, with how much time this fluid is coming, with what time the fluid is filling this measuring cylinder, right? So here this Seybold Viscometer is consisting of a tank in the bottom, which is short capillary tube. A small capillary tube is attached here to the tank, right? The tank is filled with the viscosity which we are going to measure, right? And the viscosity in the fluid, the viscosity to be determined by measuring the time, with how much time that fluid is coming outside and filling the measuring jar. The initial level of the liquid in the reservoir is previously adjusted to the standard height. First we see the what is the height in the tube, and after that with whatever the fluid is coming in the measuring tank, that how much with respect to how much time it is taking to come to certain height, certain point. So from these we are finding the viscosity of the fluid. So from the time measurement, the kinetic viscosity of the fluid can be determined by using the empirical formulas for calibrating the the calibration charts. By using this, we can find out the what viscosity is there of the fluid, right? Here measuring the viscosity, particularly petroleum products, by determining the time it takes for a fixed volume of fluid to flow through the calibrated orifice. To calibrated orifice under controlled temperature condition, it will take through a calibrated orifice under controlled temperature condition. So already we know that discharge is equal to area into velocity. So here discharge is equal to area into rise, which we are taking with respect to time and how much it is filling. R is the rise in the measuring tank, and T is the time, how much time it is taking to come to the certain point. Let us say if rise is 5 centimeters, if rise is 5 centimeters, so how much time it is taking to fill the measuring tank of 0 to 5 centimeters. By taking rise constant, how much time it is taking, or else by taking time as a constant and how much rise is taking place, how much amount, how much height, how much depth it is filling the measuring tank. Thank you. We have discussed all the measurements of viscosity.
Like, share and subscribe. Hit the bell icon for more updates.